All right, guys, I'm going to go through this homework 3, energy and thermo. I'm going to show you how to do some of the problems and kind of how to set them up, what equations to use. And then after that, I'm going to kind of let you use your judgment and see what you can do with the rest of them. I have other videos that kind of go into how to use Q equals MCAT, which is the new equation we're using this chapter. It's not really new. You did it in chemistry. So anyways, let's go ahead and just go straight to it. A 73 grams, so we're working with 14 here. A 73-gram sample of copper at 10 degrees Celsius is at 10 degrees Celsius. If 624 joules of energy are added to the copper, and you can't see because it cuts off and goes to the next page, but this just says, what is the final temperature? So T final equals question mark. And the specific heat of copper is, remember specific heat, remember capacity, is in this problem they give you, where is it? 387 joules per kilogram degrees Celsius. 387. Okay, so let's go ahead and do guess method here. I have 73 grams, but remember we have to convert that into kilograms. So we're going 1, 2, 3. So 0.03 kilograms is your mass. And the copper is 10 degrees. This is the initial T. Initial T is 10 degrees Celsius. This is important because what equation is this, right? Let's see, 624 joules of energy, so that's going to be heat, right, which is Q. Remember, heat is energy measured in joules. Anything that is in joules is an energy. Heat is energy, not to be confused, again, with temperature, right? Temperature is not the same as heat, right? Heat transfer is what occurs because there's a difference in temperature between two items. All right, so let's see our equation we're going to use. It looks like it's going to be Q equals mass times heat capacity times change in time. And I'm going to have to move some stuff around. You're going to see what I mean real quick. All right, let's see. So this is kind of the hardest example of how you would do one of these problems. You typically wouldn't have a whole lot of these problems happen like this. So let's see. Q equals MC delta T. Okay, let's do a checklist, see if I have everything. I have heat given. Mass is given. The specific heat is given. And I'm missing, how do I expand this guy right here? How do I do a change in something? T final minus T initial. Okay, cool. So I have the T initial. I'm looking for this guy. So I'm going to have to do some algebra, right? We start furthest away. So I'm going to start over here. How do I get rid of these two guys? I'm multiplying by MC. How do I get rid of MC? You know this. Divide by MC on both sides. You end up with Q divided by the mass of the object. C equals T final minus T initial. Okay, and I need to find T final, so how do I get rid of this guy? Right here, I would add it, right? T initial goes to this side, okay? So I end up with my final thing here is going to be, I'm just going to go ahead and write it up here. Oh, here we go. So we have Q over the mass times the specific heat minus the T, plus the T initial. And that would get you your T final, okay? And that's how you would do that problem. Alrighty, let's move on to question 16. All right, here's 16. Okay, so right here, this is mass. But how many masses am I dealing with in this problem? Let's see. 27 meters per second, this is your velocity, to a stop, so that your change in V would be 27 because you're going from 27 to 0. The brakes contain 16 kilograms. Oh, I have a mass, another mass, so what should I do to kind of differentiate this? This is 1, and this is going to be M2, okay, of iron that absorbs energy. What is the increase in temperature? So what were we looking for here? We're looking for the change in T of the brakes. Assume the specific heat of the iron is that, so that's your heat capacity. All right, so how would we set this up? So this is an energy conservation problem, right? So what am I given? I'm given that I have a car that's moving, so what type of energy is it going to have? It's going to have kinetic energy, right? The kinetic energy at the beginning, we know that it has to be conserved, is going to end up turning into what? Not kinetic energy final, not potential energy final, because we're not raising any of these, and we're not doing the sum of these two things either. But what are we turning it into? What type of energy are we turning this into? it absorbs energy. What type of energy are we looking for? We're looking for the Q, right? We're looking for the Q. So whatever energy is lost or actually transformed is going to be transformed into the heat energy in the brakes, right? That's the only way that it gets done. It's the only way that you're able to stop a vehicle. So we essentially have that our kinetic energy is equal to our heat. And what is our equation for kinetic energy? 1/2 m, and which object was moving? Was it the brakes or was it the car? It's the car, right? So that's m1 times velocity of the car squared equal to, what's Q equal to? M times C delta T. All right, so that's mass. Which object is going to get the heat? Is it going to be the iron that gets the heat, or is it going to be the car that gets the heat? Well, it's going to be the iron in the brakes, right? So that's M2, specific heat of the brakes, times the delta T. And what were we solving for? Delta T. All right, so this just becomes algebra now. So I have this, I have this, I have the mass, I have the specific heat, and I'm looking for delta T. So how do I get rid of mass 2 and specific heat? This is just a division, right? Whatever you do on one side, do to the other. So you end up with 1/2 m1 v squared over m2 times the specific heat of the iron. Or you could rewrite this as like this, right? You could do m1 v squared over 2 times m2c. That would work as well, and just plug in your numbers. Okay, so that's how you do problems like that. You just got to do a little bit of algebra. Okay, now we're going on to question 6. All right, so let's look at question 6 here. Some of these are kind of repeats of questions we did last week as well. Where's 6 at? There it is. When a driver brakes an automobile, I mean, not literally brakes it, but he hits the brakes, the friction between brake drums and the brake shoes converts the kinetic energy into heat. Okay, that's what we just talked about. If a 2,066 kilogram automobile traveling 33 meters per second comes to a halt, how much does the temperature rise in each of the 4? Already done this? No, I already did this one. Sorry. It's not the one we're going to do. Oh, yeah, it is. Okay. How much does each of the 4 kilogram iron brake drums do? So all I wanted to do is show you in this one is this is a similar process. We're converting kinetic energy into the Q. The Q loss becomes the energy loss here becomes the gain over here. But you need to make sure, because we're asking for how much of each of the 4, that what do you think you should do to your kinetic energy? What do you think you should do here? All right, so we're not looking for the total like we were in the last one, but since we're dividing up into 4, just remember to do this, right? Okay, so be very careful with that. Now let's look at question 4. So the 4th question we're going to do is question 2, actually. All right, so let's get rid of this guy. Oh, sorry. All right, at time t initial, the kinetic energy of a particle is 34.9 joules, and its potential energy is 4.61 joules. At some time later, the kinetic is now this, so you would expect the remainder to be potential, right? But something happened here, right? Something happened. What do you think should happen to potential energy? Well, it should be the other part of the total mechanical energy, right? So let's look at that. We did this the other day. So if we have 34.9 plus 4.61, that would be our kinetic plus potential, and that equals the total mechanical energy, right? So it serves to reason that if you only have, so this is part 1, part 2, if I only have 13.1 joules of kinetic energy, sorry, that's kind of gross looking. Let's rewrite that. So I have 13.1 joules of kinetic. I know that this has to add up to the same value as up here. This has to be the same all the way down. So what I would do is I would just take this total up here and subtract 13.1, and that should be this guy, right? Okay, and that's for conservative forces, if energy is conserved. But now let's look at the problem right underneath it. If the potential energy, so let me get rid of that, sorry. If the potential energy is only 6.5 instead, what is the work done by non-conservative forces acting on the particle. So what they're looking for there is there's something missing, okay? There's energy that's missing there. And what you need to basically know is when we did mechanical energy, in real life, it's not just this situation, right? You also lose some of the energy from the internal system here as heat, right? And that's usually going to be from friction or something like that. So just keep that in mind there. All right. There's some other problems that are very similar to the second problem I did where I was converting kinetic energy into heat energy, but they have to do with potential energy, but it'll be the same process. All right, I hope that helps.